Swayam Prabha. Digital India. Educated India.
Welcome to the module 4 of concrete technology. You may recall in module 1, 2 and 3 we discussed about the materials. Those goes into the concrete, and having done that, now we can look into the procedure of mixed proportioning. Conventionally, this is called mixed design as well. And in our discussion, the general outline of the discussion is, we'll first mention about how do you specify concrete for a given application, the mixed proportioning or mixed design procedures by and large in general, then the methods those are available. So today we will be talking about general method, method in general, and in successive classes we will be talking about various methods those are adopted. So what is the objective of the mixed design? What is the objective of a mixed design principle? First of all, to find the combination of constituents that would give concrete having properties complying with certain specifications. And of course it must do it economically, because that's the basic fundamental principles in all engineering designs or principles. Now then, one must specify the properties, right, or the characteristics of concrete, those satisfy the need at the fresh and hardened states. That is, you see, characteristics of the concrete, those satisfy needs at the fresh and hardened states, those goes into the specifications. So we must find out the constituent proportion of the constituents in the concrete which would satisfy certain properties, and those properties are decided based on certain specifications. Characteristics of the concrete are those, those would satisfy are the properties of fresh and hardened concrete. So this are the properties of fresh and hardened concrete, fresh and hardened concrete. Constituents we would select such that we get the properties of concrete with certain specifications. Now the specifications are in terms of properties of fresh and hardened state, properties of concrete. These properties are of course selected based on application and expected performance. So this is important to understand expected performance, right? So they are selected based on application and expected performance. Now we said fresh and hardened concrete properties. Although we have not looked into or not really defined various kind of properties of concrete as yet, which we shall do in our successive modules. Fresh concrete properties are specified in terms of some of those engineering characteristics called slump, VV, or compaction factor. These are some engineering properties devised for measurement of fresh concrete properties. What these values are, what are they, we'll come to this in detail sometime later on. We'll also talk about a little bit on the measurement methods. But commonly adopted one is the slump. So we specify concrete, fresh concrete properties in terms of a property called slump. And these values, what is slump, we'll come to it in our next module when we talk about fresh concrete more in details. But for the time being, let us understand that it is the height or settlement of a standard conical shape of concrete prepared in a standard manner at its fresh state. So it is settlement of such a shape concrete under its own weight. We'll see that sometime later on, but at the moment let us say slump is one of the properties, and this property is most commonly used. The method of placing, section dimension, amount of reinforcement present, this decides the property requirement. That means slump would be decided, or compaction factor, or VV time. VV, unit of VV is time. This is a fraction. All these are decided based upon the method of placing, section dimension, and amount of reinforcement present. For example, slump of concrete specified, let us say, Indian standard method. For shallow section it is very low. For mass concrete, for shallow section is very low. For lightly reinforced beam it is low, from 25 to 75 millimeter. Heavily reinforced beam 50 to 100 millimeter, and if you want to pump the concrete it should be 100 to 150 millimeter. So these are given in code. For example, Indian Standard Code of course is IS 456 2000. So Indian Standard Code is IS 456 2000, and these are specified in such code. Alright, so this is how we express or we specify the properties of fresh concrete. Hardened concrete. Since concrete is a structural material, we specify the grade of concrete in terms of its compressive strength at certain age, because in the module 1 we have seen that reaction of cement with water produces a material which is stone-like, but this formation of this hardened material from a plastic state takes time. First it solidifies and then gradually it gains strength. And this process of strength gain takes time, quite often could be months. It has been standardized, age has been standardized for measurement of compressive strength in, through standard samples or specimens at the age of 28 days. So we measure the compressive strength of concrete at its 28 days age, but not necessarily always we will specify the concrete strength alone at 28 days. We might specify it at some earlier age also, depending upon the requirement. For example, in some cases we might specify this at 7 days. We might specify it at 7 days, 7 days or 1 day. Grade of concrete is always defined with respect to 28 days compressive strength. Generally, in Indian scenario, we test cubes, and we'll talk about that sometime later on. Why? How concrete strength is affected by the specimen size, shape, etc., etc. So, in Indian scenario, we talk in terms of grade of concrete, measuring the strength at the age of 28 days, compressive strength at 28 days, and we specify it in terms of something called characteristic strength. Characteristic strength is defined as that strength which would be exhibited by more than 95 percentile of the cubes. We might also specify the concrete strength in terms of its tensile strength at certain appropriate age. In some cases, maybe we are designing for, tensile strength of concrete. Sometimes, let us say, in water retaining structures or where flexural strength becomes very important criteria, let us say in pavement, we might specify the the concrete in terms of tensile strength also, flexural tensile strength also, in addition to 28 days compressive strength, 28 days compressive strength and grade. But this is not all. Concrete must remain durable or must be able to endure the environment to which it is exposed to over a long period of time, right? And that is related to its durability. Durability is the property by virtue of which the concrete can withstand the environment to which it is exposed over a long period of time. So, although at the moment most of the codes don't quantify the durability in terms of, let us say, service life or something, but we understand durability is a property related to its endurance to various kind of exposure conditions. And our understanding in terms of quantitative way of understanding this durability property is limited. At the moment, from the knowledge of the mixed proportion and knowing the exposure condition, we may not be able to say how long concrete would be able to perform as required. It must perform, it must be functionally satisfactory, it must exhibit functional performance, satisfactory functional performance. Performance would mean that it should be able to carry the load, satisfy all other serviceability requirement, shouldn't show excessive deflection, cracking, etc., etc. So performing satisfactorily for a period. Now, but this period is not really known to us at the moment, or rather we cannot calculate it out very precisely with the current state of knowledge of concrete. Therefore, most of the codes or all codes actually till date specifies some prescriptive measures, or rather recommend some kind of prescriptive measures in order to ensure adequate durability performance during the intended design life, all right. So durability requirements therefore are specified, or rather, they are specified in terms of some prescription of cement, minimum cement content and maximum water cement ratio, or minimum grade of concrete, etc. Minimum cement content, maximum water cement ratio and minimum grade of concrete, etc. Minimum grade of concrete, etc. All right. Okay. So what we have seen, we specify concrete first of all in terms of fresh concrete property, and a common way of doing that is in terms of slum. We specify also concrete in terms of its grade, which is generally related to 28 days or characteristic compressive strength at the age of 28 days. We might specify strength of concrete or hardened properties of concrete in terms of strength at some appropriate age, maybe earlier age. Some cases we will require that. For example, where we want to do early demolding, right? Say a pre-tensioned precast system where I would like to apply some pre-tension to the concrete, expose it to some kind of pre-tension. In such situation, I might require high early strength. So in addition to grade of concrete, I might also specify the strength at some early age. Some other cases, I might specify tensile strength of concrete at, let us say, at some age. Then comes the long-term properties at the hardened state. At the moment, we have some prescriptive recommendation given in codes, namely, we specify minimum cement content, maximum water to cement ratio and minimum grade of concrete to ensure adequate durability of concrete. Now, why water cement ratio, why minimum grade of concrete, and why minimum cement content and maximum water cement ratio? All this will be understood when we talk of durability of concrete sometime later on in some additional module. So at the moment we are trying to look at the mixed design. So this is how we specify the concrete, and once these specifications are available, some more additional information may be needed. These additional informations are nominal maximum size of aggregate, which is again decided by the spacing of the reinforcement, the section, the cover, and also somewhat related to the strength of concrete. A high strength concrete may be relatively more easily designed with lower maximum size of aggregate compared to, let us say, a low strength concrete which can consume even the larger size aggregates. Okay, the reasons we will explain and we will understand sometime later on. But what at the moment we want to understand is the maximum size of aggregate is an important information one would need to do the mixed proportioning. All right. Then whether the aggregate is rounded or crushed. Natural aggregates are generally rounded, as we have seen earlier, and we have seen also that shape governs the packing characteristics of aggregate, because we have talked about aggregate material and rounded or crushed, and we know that rounded aggregate packs better than crushed aggregates. They are grading the proportion in each size, and that's what we have seen. If we, depending upon the proportion, the packing characteristics of the aggregate depends upon the proportion of each size that goes into making of the or packing of the aggregate themselves. Similarly, for sand, the grading zones may be important. Again, that's telling us what is the size fraction belonging to which size, proportion belonging to each size fraction. That is what it is. Fineness modulus, also we have discussed sometime earlier, is again related to the kind of a measure of an average size. So size of the aggregate, their packing characteristics, proportions in, packing characteristics are governed by shape of the aggregate, maximum size of aggregate, and proportion in each size. These informations are important. Now these are important from the point of view of availability of aggregate, because one would like to use locally available aggregate to minimize the cost of the concrete and all other transportation related negative aspects, for example energy consumption in transportation and so on and so forth. So one would like to use locally available aggregate, and therefore what is the size fractions available. If there is anything missing, such informations would become important in mixed design. But we have already seen how this MSA affects the packing characteristics of aggregate, how shape of aggregate affects the packing characteristics, and its effect on fresh concrete, etc. we'll understand, of course, later on. One more information is important, is the specific gravity of aggregate, because volume occupied by unit, volume occupied or mass in unit volume, this is what unit volume of the aggregate. So volume to mass ratio is through specific gravity, and therefore this is also an important information. What we do is we actually measure this before doing the mixed proportioning or before doing the mixed design. We generally measure this if this information is not available. We'd like to know type of cement, and cement strength is not a necessity these days. Cement strength is not a necessity. Cement strength is not a necessity. This is not a necessity, but some of the codes might use cement strength as an input to mixed design. In fact, earlier Indian standard was using this cement strength as an input, but now it is not a necessity in Indian code, that is 10262. Indian code 10262. So IS 10262. This is not a necessity anymore. This is not a necessity anymore, but earlier the code was using it. So that's why this appears here, but by and large we don't need this information now. Now type of cement is important, particularly related to durability. Well, this information is important in the sense that from the point of view of minimum cement content, this has got some importance, not really much, but what would be important for us to know from our possibly past experience or from our record, how much is the strength, kind of strength to water cement ratio relationship for concrete, that becomes an important issue. Anyway, type of cement may be specified, because this is what you would be using. So if you have to do a trial casting, you have to use that particular type of cement. If I am using some admixtures, what is the kind of admixtures I am using, that information is important. and its compatibility with the cement and the other system, overall system, that is also an important aspect. Absorption of aggregate and moisture, absorption of aggregate and the moisture content of the aggregate. This is an important information. This we will have to know. We measured the moisture content at what is called saturated surface dry, SSD condition, which we have seen earlier. Earlier we have seen. So we measured the moisture content required for attaining SSD condition from bone dry to SSD condition. What is the moisture content? How much is the moisture content related to SSD condition? That's the information is important, because in actual site moisture content may be different, so you have to do some adjustment accordingly. And then this is an important information, degree of quality control that is achievable at the site. This is an important information. Standard deviation, we'll discuss this a little bit more in the next couple of slides. So degree of quality control or control that is achievable at the site, this is very important. Remember, grade of concrete is always related to the site situation. Although concrete is prepared and tested in the laboratory, which can be a site laboratory. Very well, it should be a site laboratory. Now, the site laboratory should take account of actual control available while production. So that's what the degree of quality control is important. Why it is important will become clear as we go through our next couple of slides. How do we fix this? This we fix based on recommendation of relevant standards. Like we said that the slump is given is IS 456-2000. For, let us say, pumpable concrete, it should be about 100 to 150 mm. In fact, 120 mm or 130 mm is possibly the minimum good slump at which pumpability can be achieved. So relevant of the standard is very important. Recommendation of the relevant standard is very important. So we select these specifications based on recommendation of the standards. In India, of course, mostly we do it based on IS 456-2000. At the moment, we do with respect to this one. We do it with respect to this, right? So in any other country, they will have, all other countries will have their corresponding standards, and accordingly it will be selected. Now these specifications must be realistic. What is achievable? So it must be realistic. It should be achievable. They must be non-conflicting, non-conflicting, two specifications. For example, specification mentioned in case of durability should not be conflicting with something else, some other specification. So this would be very important. They should not be conflicting. Conflicting specifications should not be there, and they should be realistic. Guidelines of the codes are usually taken, relevant standards and code, and then it must be discussed with all parties involved before fixing the specification. Let us say contractor, the man or the group which will be actually doing the job at the site, construction work, execution of the construction, the designer, maybe even depending upon the situation, even sometime the owner may be also involved if they are knowledgeable. So all contribution of all the people involved, that should be taken into account, and then these specifications are finalized. And obviously previous experience in the similar site plays a big role. So specifications are fixed according to this kind of this past experience, codes, ideas from everybody involved, and so on and so forth. Now, on what does the fresh concrete property depend? Well, this we'll talk in details in the next module. But we take it for granted at the moment that it depends upon mainly on paste content. mainly on paste content. We can understand this. Sometime perhaps when we are talking of aggregate, we have discussed that they should pack very well. Now, the aggregates themselves are not, moldable. Fresh concrete properties relates to moldability. I should be able to mold it easily, and fresh concrete properties relates to moldability. How can I mold? Molding process involves essentially driving out the air from the concrete, because fresh concrete when I place it, it contains about 30% air voids into it, right? Normal concrete, they will contain around 30% air void in it, and this has to be driven away. Then second issue is, seldom it is in the location where final, it's in the shape, it is not in the shape of the mold itself. So there has to be some flow to acquire the shape of the mold itself. So therefore, we must drive out the air, and also it must acquire its shape also. That means that some mobility is needed, and by this process of mobility, the aggregates and the concrete itself should get placed into the mold in its appropriate position, and air must be also driven out. This is best done by vibration. This is best done by vibration in normal concrete. Of course, there are special concrete called self-compacting concrete, which are becoming popular and popular nowadays. But in normal concrete, we adopt vibration in order to drive out the air and get the shape of the concrete appropriate, same shape as we desired, the desired shape according to the mold. Therefore, concrete must be able to flow. It must be able to flow. Now, this flowability, if we look at it, aggregates are not flowable. They are stones, and they themselves are just not flowable. Okay, they can little bit flow, move and form a heap. They have an angle of repose, right? They can form a heap, and they'll form heap like this, and they will have what is called angle of repose. So some angle of repose where this sort of an angle, where some, it will have some sort of angle. So they can form an angle, from a heap. Now, paste. So therefore, if I vibrate it, they may not move a little bit, but not much. But if I have paste inside them, paste in the aggregate system, this paste are easily flowable because they are more of a plastic state. So aggregates and paste together is in plastic state, and it is the paste which is easily flowable. In fact, in the paste again, the water is most easily flowable. So if I have small amount of paste within the aggregate, it is not going to work. I should have sufficient paste which will fill in all the voids within the aggregate system, and when I put a little bit of vibration, the paste themselves should be able to move and also take the aggregate along with them. So therefore, paste content is an important issue as far as the fresh concrete properties are concerned, right? It depends upon water content, and paste. In the paste, the main thing which is actually flowable easily, or which causes the getting into the new shape under vibration, it is the water. Okay, we should see this sometime later on. So paste, water content, or in other words, paste content is the most important thing which dictates the flowability or moldability of the concrete, and therefore fresh concrete properties is largely governed by moldability. The other issue, of course, is it should remain plastic during my placing and compaction. So that is related to what is called setting properties. We have seen setting properties of cement. Setting properties of concrete depends upon the setting properties of the cement, all right, but it also depends upon the setting characteristics of the admixture that I have added, because some admixtures can retard. That's what we have seen when we talked of admixtures. Some admixtures can retard the setting of concrete. Therefore, in concrete, setting properties of concrete is governed by properties of both cement as well as the properties of admixtures they control. So it should remain plastic during the compaction up to the compaction stage, complete molding stage actually, up to complete molding stage. all right, and it should be easily flowable. Now these properties are dictated by paste content and water content, mainly water content and paste content, right? And I wouldn't like to keep too much of paste because paste contains cement, which is the costliest of all the materials, and therefore, you know, if I have too much of paste, the cost of the concrete will increase in normal concrete. So I'd like to keep the optimal quantity of paste and yet get the right kind of moldability related properties. That is, slump is one such property. So optimal quantity of paste means water as well as fine materials such as cement, fly ash and similar other material. Right. Now that would be ensured, if I want to keep minimal material, that would be ensured by packing characteristics of the aggregate. If they pack very well, you remember we talked something of packing density, which is the mass of solid in, let us say, unit volume of the bulk material. So 1 minus, mass or volume fraction, sorry, it is the volume fraction of the solid material unit volume of the bulk material. So 1 minus packing density gives me the void content in the aggregate system. So this void content should be minimum. That means I should have best packing. And good old days, ideas of these packing densities were relatively less known because science of particulate matter was not so well developed. So we talked in terms of, and we understood, of course, it is understood by observation or empirically, that if I add different proportions of different materials, it packs better, and appropriate proportions of each fraction of each size fraction would make the packing better. That's what we have seen while discussing about aggregate. Therefore, grading of aggregate is an important issue. Grading of aggregate is an important issue. Grading means proportion corresponding to each size. That's a very important issue. So grading of aggregate, and we have also seen as I increase the maximum size of aggregate or number of sizes, if I increase, my packing density improves or the void system in the aggregate improves. So good grading, higher MSA, they will always reduce down the void system in the aggregate, and therefore my paste content required for right kind of or appropriate kind of moldability or workability would be less. So it will make the concrete economic. So paste content or water content, they are dependent on the grading of aggregate and maximum size of aggregate, all right, and also on shape of aggregate. We mentioned earlier that rounded aggregate packs better, therefore you will require lesser paste. I repeat, rounded aggregate packs better. That's what we have seen when we talked about aggregate. Therefore, we will require lesser paste for the same workability. So concrete would be economic for the same workability. The strength is not governed not by shape. If anything governs, it would be a structure of those aggregates, but not by the shape. Shape governs the packing characteristics. So these are the factors which will dictate how much is my water required or paste required, and for water required is decided on this aspect. Strength is mainly governed by water cement ratio or water to cement and fly ash ratios. Strength is largely governed by water cement ratio or water to cement and fly ash ratio. All other properties can be related to compressive strength. All other properties can be related to compressive strength. All other properties can be related to compressive strength. I mean all other mechanical properties. Empirically, for example, modulus of elasticity as we measure, right? Elastic modulus used in design, they can be related to compressive strength. Even flexural tensile strength can be empirically related to the compressive strength. So largely we design concrete for compressive strength, only in special cases for tensile strength. And water cement ratio governs this. Why does water cement ratio governs this? because water cement ratio controls the porosity and pore sizes of cement paste we have seen. Even in concrete, same thing happens. We have seen in the case of microstructure development of cement paste, it is the water to cement ratio which governs the capillary porosity. Higher water cement ratio means more capillary pores. Therefore, strength of the concrete, which is a function of the porosity and pore sizes of concrete, is governed by water cement ratio. We shall see this in detail sometime when we talk of strength, the factors affecting strength of concrete. That time we shall see this and we'll understand more about it. But at the moment we understand it is the water cement ratio which governs the strength of concrete, and therefore, or if you are adding some other supplementary cementitious ratio like fly ash or let us say silica fume, the ratio of water to cement plus those ones would actually govern the strength. Now we also understand that deterioration process in concrete takes place through ingress of material from outside, and again through those pores and interconnected pores. Therefore, porosity governs the strength again, durability again, or deterioration again. So porosity governs the deterioration, and therefore durability aspects are controlled through again water cement ratio or water cement to fly ash ratio and grade of concrete, etc., etc. So water cement ratio is an important factor which governs the durability as well as strength, because we are prescribing maximum water cement ratio. So mixed design procedure, first thing is we determine actually water cement ratio from the strength requirement and durability requirement, or durability requirement, whichever gives me the higher value of lower value of water cement ratio, that's what I will select. Let us see, controlling one will be the lower value. Let us see the procedure then, mixed design procedure. Then, but before that, just one more thing I would like to understand, or rather I like to make clear, is that I should design the system for minimum cost, satisfying a set of specifications. So I am minimizing the cost. Therefore, it is an optimization problem. Minimize the cost, minimize cost. It's minimize cost. This is a problem of optimization. In fact, in classical optimization problem, we either maximize the profit or minimize cost, or maximum gain, minimum losses, or whatever it is in classical optimization problem. And I would have loved to formulate mixed design process as an optimization problem. Then I have a software and I am through with it. Just put on those data and you get the output as an optimization problem. In many cases it is used. Many engineering problems we can use this optimization process. Mathematics of optimization is very well defined in mathematics. But to do that, usually in an optimization process, I'll have some objective function or some objective, like here the minimization of cost, and cost of each component of the material if I know, then total cost I can always minimize. Subject to certain constraint, let us say my strength must be greater than specified strength, slump must be greater than specified slump, etc., etc. So these are certain specifications can be formed in terms of constraints, what we say in case, what we usually mention in case of classical optimization problem. So my specifications could have been constraints, my objective could be minimization of the cost, and I could have easily done an optimization process mathematically, and it would have been a very good thing, very easy situation. But unfortunately, we don't have well-defined equations relating strength and mix factors. Neither we have very well-defined equations relating slump and mix factors. So well-defined mathematical relationships are not available. In fact, if you look at a book by Sandor Popovics, he has listed down as many as 50 plus equations for slump of concrete related to various factors. Now, what does it mean? They cannot be general. A general equation satisfying all the conditions would have been only one. Like one Newton's law can express or can be, all motion equations, all motion or movement of or moving bodies, behavior of moving bodies can be expressed in terms of one general equation. We don't have such general equations for slump of concrete. That's why there are 51 equations. Each was developed empirically for maybe for the specific condition of that particular experiment. So we don't have general equation. Therefore, we can't treat it as an optimization procedure. We don't have well-defined relationship, neither for strength, not for workability, and durability is out of question because we are only at the stage of prescriptive level now. So what we have? Empirical formulae and experience. Some empirical formulae, not very general, but still some formulae is available, and experience of people. Therefore, we can't formulate it as a mathematical problem. And even if we do, it will be case specific. So use of very sophisticated softwares, etc., really doesn't make at the moment. They are not very much conducive. In fact, finally you have to make a trial mix. So we must understand that mixed design procedure is largely empirical in nature, and it is not only science, it has got a large arts component. A person who does mixed design day in, day out for a given type of aggregate and cement system or various cement system in a particular locality, he or she will come out easily with a mixed proportion for any grade of concrete under that situation. Because experience is very, very important. Very, very important is the experience in this at the moment. Because we don't have generalized relationship and materials varies from place to place, and even from the same source if you are getting material, you will find that the properties of the concrete vary. So experience plays a very, very strong role, and mixed design procedure always involved some trial casting. The mathematics or procedure, mathematics is very little, there is hardly anything. The procedure involved is only looking at few charts and tables and coming at the proportion, starting proportion. But finally you have to do several trials and come to the best. So it is more of an empirical sort of an procedure, and therefore it's more of arts, and the science is obviously there, but there is a good lot of arts is also involved, and one must realize this. Right. So mixed design is more of an art together with the science part of it. Now let's understand the procedure. To understand the procedure, first thing I must understand is the nature of variation of concrete strength. Supposing I have a concrete strength, I thought the mean strength would be somewhere, let us say, somewhere 28 days age I am talking of, or at the moment let us say 28 days. I decided that it should have some kind of a mean strength of, let us say, 55 or so. For this will be valid for any other mean strength also. I'll find that if I test large number of cubes and plot a frequency diagram like this, then good lot of majority will show the strength close to what I have actually conceived as a mean, but possibly large number or 50% of the strength would be lower than that, and 50% of the strength would be higher than that. This is because compressive strength, cube compressive strength at the age of 28 days depends upon too many factors. There are too many variables. For example, it would depend upon the error in mixing, proportioning. First of all, what we call batching. There would be some kind of error in batching. You wanted to put 180 liters of water, you might have, your measurement system would have meant it to, you might have put it around 180 instead of 185 or 190 instead of 185. There will be some tolerances about the actual quantity, specified quantity of water you want to mix. Similarly, quantity of cement you wanted to put in, let us say is 320 kg, just of the cement you want to put, you might add up actually 310 or 330. It is very difficult to put or ensure absolutely same quantity of cement time and again. It will vary within certain tolerances, allowable tolerances, and therefore you can see that water cement ratio would vary from a mix to the other mix. Even in the same mix, the mixing procedure itself could add to variations. First 15% of the discharge from a mixer machine may not be exactly same as the last 15% of the discharge from the same mixer machine. So therefore, there's a kind of variation, strength variation that could occur because of mixing. Many other factors like aggregate in one batch might vary from the other batch. Aggregate in a given cube might vary from another cube which I have molded for testing. So therefore, there are several such factors which govern the strength, finally you measured strength. Even the testing machine, interaction with the machines, every time the load it is showing, there are some errors in load measurement, there will be minor errors, random errors. So there are too many random errors which control the strength of cube strength as measured. And statistics tells us from central limit theorem that in such situation a random variable which depends upon number of random variable will vary normally. That means it will exhibit a bell-shaped curve as shown here. It will exhibit a bell-shaped curve as shown here. The strength, although I want it to be 55, it will actually vary from 45 to 65 or 67 to 43 to 67, and therefore there is a range over which it varies. Hence, when I specify my strength, my specification of strength actually goes in terms of, this variation is normally distributed and average represents what is called mean, and it will have some kind of dispersion about this mean. Just if you recall that we defined, and this also comes from statistics, that whole of this area under this curve, if I consider to be 1, then 50% of the curve is on this side, 50% of the curve is on this side. In other words, 50% of the results will be above this mean, which is the average, and 50% of the result will be below the mean. 50% will be above the mean, 50% will be below the mean. Now we have defined our characteristic strength is that strength which will be exceeded by 95% of the cubes. Therefore, I must define my characteristic strength accordingly. Now, this is what we will do in the next lecture. So, to sum up, what we have discussed is how do we specify the concrete? How do we specify the concrete for mixed design purpose? 3 issues we have looked into. One is the stress test properties, which you said is slump is most common. Then we looked at the strength properties, and then we also specify it in terms of durability requirements which are prescriptive, like maximum water cement ratio limit is given, minimum cement content, etc., etc. And then we just try to say why this, little bit of why, and what are the factors in the mixed proportion that govern this property. For example, we said water content or paste content will govern the slump, fresh concrete properties. Water cement ratio will govern both the strength and durability. Therefore, from the strength we would like to fix the durability, from the strength we would like to fix the water cement ratio, and from durability we will try to fix the water cement ratio. Whichever gives me the lower water cement ratio, that's what I'll select, and from the slump requirement, etc., I will fix the water content or paste content. We shall see that in the next class. To start with, I just started about how do we decide, how do we define. To start with, how do we define the grade of concrete, and in the next lecture we'll start from here. From the grade of concrete, and then overall mixed design procedure will will explain, followed by some of those methods. Thank you very much.